the YouTube web streaming. So, dear colleagues, today we have a new distinguished guest. Well, not really guest, a member of our intense community, Professor Nguyen Li Phuong. Sorry if I made mistake in the pronunciation of your name. Still, Vietnamese characters are a little bit challenging for me. I need to take some time to learn them better and to understand how to call people without offending them. Sorry. Nevertheless, the researcher with impressive CV and with deep experience in the lecturing topic. And today's topic is in particular important this day. And like air pollution is recognized as one of the greatest health threats, and when it's so important for us to understand actually how air pollutants behave also in human body. And with this, I'm giving you the floor. Let's enjoy the lecture, and please make note of your questions. I'm hoping for a nice discussion at the end, by the end of the lecture. So please, the floor is yours.
Yeah. Thank you very much, Professor Anton. Am I correct? Professor Anton, right?
Well, that's my first name. But yeah, it's more or less okay.
Yeah. Okay. Thank you very much for your kind introduction regarding this lecture today. Yes, I'm very honored to be here to share with all of you regarding our research result recently, and also for the past 10 years. Yes, for the study topic today, I would like to share my PPT file.
Yeah, please go ahead.
Yeah. Just a moment. I'm looking for share screen. So I share already my PPT file. So
yeah, we can see it on the screen. So you make it like full screen, and then you can go ahead.
Yeah. Okay. I will make a full screen.
Yes.
All right.
Okay, it's perfect now. So please.
All right. So yes, I'm very happy to be here to share with you about my research team regarding applied particle image, velocimetry, and computational fluid dynamics methods to study the transportation of airflow and air pollutants in human airways, and also the human bodies as well. I'm Phuong from Ho Chi Minh City University of Natural Resources and Environment in Vietnam. Not moving just a moment. Okay, the first part I would like to introduce the indoor air pollution and human airway system. As may we know, the outdoor environment, especially recently. Can you hear me? Yes. Okay. May I continue? Yes, the outdoor environment and also outdoor pollutant is also important. But however, recently we found that the duration time of people stay indoor around 80% of our times. So the occupant living in the indoor environment also can expose to the high concentration of the indoor pollutant that may transport from the ambient air to the indoor, and also the indoor sources. So in this part, I would introduce about the indoor environment problem. The concept of indoor air quality first introduced among scientific community in last 3 decades due to some occurrence of episodes indoors. As central headquarters of U.S. EPA, Environmental Protection Agency of United States, building in Washington, D.C., more than 100 people fell sick within 15 minutes of entering the office. And this symptom, where we call that's building six building syndrome. And in LA, the carbon monoxide concentration in most of the well-insulated building were 3 times greater than the outside level. So this is rising the concern of the people, of the population regarding the indoor air pollution. So what's called indoor air pollution? At first, the air tightness of building. It means that we are not creating the ventilation rate enough for the people breathing. This is we call air tightness, and the poorly designed air conditioning and ventilating system. And also the indoor sources of pollution, like we can cooking, we can make other office equipment like printer, photocopy machine. It will emit a lot of air pollutants. And also the outdoor source transport from the traffic, from the transportation, from the industry, from the air outdoor. So we identify the indoor air pollution source. It can find in some in any area in our building. So we say indoor air pollution if indoor air is contaminated by smoke, chemicals, smell, or particles. In the WHO accounted for 3.8 million deaths are attributed to indoor air pollution annually. This is the number from the figure from the WHO. We can find the air pollutant in the building material like formaldehyde, benzene, TVOC, from cement, from bathroom, from floor, from furniture, from carpet, from paint. Yeah, they are emit a lot of air pollutants. And also we call PM 2.5. This is one of respirable lung particle. This can cause cardiovascular disease, lung cancer as well inside our building. And also we expose to a lot of various kind of chemicals, particle inside the building. It can cause the health problem. So the health effect went from the coughing and bronchitis to heart disease and lung cancer. So this is a list of disease related to the inhalation exposure to the indoor environment and also indoor air pollutant. At first, we can see the respiratory infection, and the second is heart disease, and the third is stroke, and also related to premature death, asthma, respiratory infection, and so on. And recently, we found that the pandemics of COVID-19 also transmit people to people in the air via the air. Regarding the human airway system, we breathing around 20,000 times per day, but we didn't realize that that kind of activity is so important to us, more than eating or drinking. But mostly we forget it, this activity. So recently, the COVID pandemic reminds us we inhale a lot of air, and also the virus can transmit from the air to our lungs and cause up lots of problem for human health. Of course, we know we breathing the air, we inhale the air, and in the air we got the oxygen. So without the oxygen transport, we might die in a few minutes. So this is one of the essential activity for living. This is breathing. And human respiratory system is the organ that's to help us to exchange the gas with the environment. yes, as I mentioned, we breathing 20,000 times per day. So the breathing rate at rest around 12 to 15 times per minute, and the tidal volume at rest 0.5 liter. It means that one time we inhale, we will take 0.5 liter of air. Of course, when we do more physical exercise, it takes more the volume of air and also the oxygen. And the average person breathes around 10 to 25 cubic meter of air per day. So our human respiratory system is really complicated, consisting of the nose, mouth, trachea, bronchial tube, lung, bronchioles, and alveoli. So we can see that now the picture on the left hand side. This is the human airway system I built up from the CT image. I will mention later. And the lower figure is cilia and alveoli. This one of the system down to the upper airways. And the respiratory system defense mechanism, they can help to protect us from the inhale of the oxygen and also the foreign material. The first function of the nose is regulates the warm or cool the temperature of inhaled air. Yes, and the second is moisture, the inhaled air, to protect our lung from the outdoor temperature and also outdoor moisture. And the small hair in the nose might trap the particle for evacuation. And I would like to introduce we call it in silico model. It means that the model makes for a computational simulation. At the left-hand side, the compute tomography image we talk from the Asian guide 1.7 meter and yes, Asian. And for on the right hand side, the three-dimensional reconstruction of the human airway from the CT image. We can use some software to make this three-dimensional model like this. This in the blue one. And you can see from the nose, nasal cavity, and trachea, and also the sixth generation here down there. Okay, so let's me introduce about a little bit of fluid dynamics. This is a brief review of the history for fluid dynamics. The first, Archimedes found the famous buoyancy force in the 287 to 212 before Christ. Yes, and this is very important for fluid dynamics. And the second the second person might very famous to us. This is the Leonardo da Vinci. He is a genius born in Italy, and his scissors inquisitive mind and unique imaginative power produce many sketches, fantastic plans of machine, precise dissecting diagram of the human body and fluid flow sketch, and which are still working with nowadays. And he invents the techniques that's called flow visualization. And Da Vinci was a great pioneer who initiated the door of the hydraulics. And many great researchers appear in hydraulic bloom from the 17th decade to from 17th to 20th centuries. And Isaac Isaac Newton also discovered the principle of gravitation when he looking for an apple drop down in front of him. And we should count for the fluid dynamics when we're talking about a Reynolds number, right? A Reynolds number, we can talking about the characteristic of the fluid flow, laminar rhythm or transitional rhythm or turbulent rhythm. It depends on the Reynolds number. So Reynolds is also very fabulous guy to teach us about the fluid dynamics. And the last one, the last but not least, this is the Navier and Stock. These two scientists introduced viscous transport into the Euler equations, which resulted in the Navier-Stokes equation, very important for us right now, nowadays. Yes, let's talk a little bit about the fluid dynamics. The fluid flow is commonly studied in following approach. The first is theoretical fluid dynamics. This is an analytical study of fluid dynamics generally require considerable simplification of the equation of fluid motion. The second is experimental fluid dynamics. And the third is computational fluid dynamics. You can see on the figure, the left-hand side is the experimental fluid dynamic we can do in the laboratory. And the right-hand side, the simulation image from we has done by the computational fluid dynamic techniques. So we call this case study both-way interaction from ansys.com website. Now let's go to the main part. One of the important part of this lecture. This is experimental fluid dynamic. This kind of experimental work stick it to me more than 10 years. I have done this 10 years ago, and it's continue until 5 years later. And this is my first project in a PhD course regarding a vertical duct, which you can see on the slide. And this is the visualization area of the vertical duct. One is the straight duct, and one on the left side is straight duct, and on the right hand side you can see there are a small buffer inside the vertical duct. So we call vertical duct with buffer plate. And we use the scan video camera to store a pair of images of tracer particle on separate frame for the illumination with the interframing time from millisecond to microsecond to capture the tracer moving inside this visualization region. So after we calculate all of this area, we can calculate to the velocity vector. And on the screen is now on the left hand side the velocity vector of the vertical duct, straight duct. And on the right hand side is the velocity vector of the vertical duct with buffer plate. And we can see the vortex. The vortex occurs here. The vector velocity moving this way, and on this side also due to the buffer effects. And furthermore, this is one of the sorry. Okay. The video doesn't work in this slide. Okay, so we move to the next slide. This is the base. I would like to introduce the basic idea of flow measurement. We can see the photographer at this moment at this location, and he can take a photo for the first frame. and then when he take the second photo, so we got the photo from the first frame and the second frame, and we know the time between two frames, so we can calculate the velocity due to this displacement. So this is the basic idea for the flow measurement. Yes, let's talk about the particle image velocimetry. This is a non-intrusive to a three-dimensional and instantaneous velocity measurement technique. And the particle in flow scatter the laser light here. This is the camera. This is the fluidic flow, and the tracer. This is red dot is a tracer moving inside the interested area. This is the rectangular here is the interested area. And to visualize this area, we use the laser generator. And when we operate this system, the fluid moving and the tracer moving pass through this area, and the camera can capture the tracer moving due to the laser sit here. And two images or multiple images will be taken within an interval times delta t. So after the camera took the photo, and it will transfer the data via synchronizer to the computer, and from the computer we can see the frame 1 t equal to t0, and frame 2 t equal t0 plus delta t. So based on this moving and also the delta t, we can calculate the velocity vector of inside this interested area. For the PIV component, we need as first tracer particle, second working fluid. We can set up like airflow or the water, and also the light. We need a light sources, light optics, camera, measurement setting, and also the post processing on computer. And because of the interested area is quite large, and we need to divide into the very small square. So we call it interrogation division. We divide the image pair in the interrogation region. So this is we call it interrogation region. And it's the uniform, and based on divide into small region like this, and then we can compute the displacement, and we can repeatedly from this interrogation to this interrogation and the next. In order to ensure the signal, the signal of this calculation, we need to identify the image density. The image density represents the mean number of particle image in an interrogation region. So the image densities can calculate based on the tracer concentration, and also the lysis thickness, divide for the image magnification, and multiply for interrogation spot diameter. So low image density should be less than 1, and so we call it particle tracking velocimetry. If the high image density, we can call particle image velocimetry. And this step tells us about the finding correlation. For example, this white dot, this is the first frame, and the second frame we can collect by the black dot here. So we have one white dot here, and we should calculate the correlation of this tracer from here to this side, or from here to this side, or from here to this side. So we can make it based on a sum up on possibility like this. We should find a good signal, and we find a possible match. It means the particle can match with a number of candidates within an interrogation area. This is number of candidates here. And each match has equal probability, but only one match will be correct. And only the matching particle image pair will add up, and a subpeak will appear. This is a subpeak will appear. That reflect the displacement of the particle image pattern. So based on our calculation, we can define the subpeak will appear like this. This is green one, and this is the correct one. From the fluid moving from this side to this side, and the tracer or the particle moving like this, and we can find the best match here. Yes. And this is the equation to calculate the cross correlation. This can express as follow. In this is integral for I1 and I2. This is our interrogation area and of the total frame. And X is the interrogation location, and X plus S is the shift between the images. And for the spatial correlation can be separated into three terms. This is the mean, RC is mean background correlation, and RF is correlation between mean and random fluctuation, and RD is correlation of displacement. And this is the this is RS and RC. And RF and RD. We can see RD, we can identify the correlation due to displacement, and we can see the peak mean displacement. Of course, we are calculating the right movement, the right correlation, and the other one is the noise that can affect to our calculation. And the PIV application can help us, PIV method can help us to measure the fluid flows and study the turbulent structure. We can find the helicopter blades, and nowadays there are lots of PIV study for the helicopter movement, and also the plate rotation, And regarding the unsteady of periodic flow, unsteady or periodic flows, the transient flow details, transient unsteady flow, and also complex steady flow field, and extremely low velocity flow field. Yes, and various applications as well. And of course, they have some advanced and disadvantage. The advantage of PIV is a entire velocity field can be calculated, and capability of measuring flow in 2D or to 3D space. And the equipment is non-intrusive to flow and a high degree of accuracy. In the past, before we apply the PIV measurement, we always use the anemometer. We measure at the point, and it's just 1D. And the advantage of PIV, we can measure in the 2-dimensional compared to in the past only 1-dimensional measurement. And the disadvantage of PIV is require proper selection of particle. Yes, we got a lot of problem to select the particle size. For example, 10 micrometer or 50 micrometer, we have to test. And of course, the particle for our measurement is also very expensive. And the size of flow structure are limited by resolution of image. And also, this is an expensive system. Yes, so the experimental data is really important to help us to understand the phenomenon or phenomena occurs in the real condition, real environment. And here, this is the application of PIV to investigate the flow pattern within the human airway system. Yes, this is a schematics representation of in vitro experimental setup for PIV measurement. Yes, this is built up by me 10 years ago. Yes, 10 years ago. Yes, you can see the human airway insert into this system, including the camera, and this is the tank. This is the hermetic chamber tank here, and this is the working fluid inside, and this is the pump, and this is a control flow meter. This is the flow meter, and yes, this is the controller with the valve, and this is the CMOS camera to took the image for PIV system. Yes, this is the real model because we got the CT image. We build up the computational model of the human airway here, and then we can print it out by 3D printer. Also, 10 years ago, we did for 3D printer in Japan. And on the right hand side is the working fluid inside working system inside inside a laboratory, and you can see this is in the dark mode. Yes, this is the prototype model creation, and so the testing system. On the right hand side is the PIV recording parameter. For example, here we can see the field of view 26 by 52 millimeter, 500 to by 1000 pixel. And we have got the recording methods. We have a single frame, single exposure, equidistant time interval is 2000 millisecond. And recording length, recording frequency, F here we do 500 hertz. And illumination by continuous wave, we use diode pump solid state, we call DPSS, and this is a green laser. And observation distance around 30 centimeter. And we use the program to control the system, a dynamic flow manager. And interrogation area we chose 32 by 32 pixels. And the algorithm for calculate the velocity vector, we use the adaptive cross correlation methods. And finally, total number of vectors around 1444. And seeding material, we use hollow glass sphere. And on the small figure is we try to calculate the refracting index matching because this is the acrylics material, and we need to make working fluid had the same refracting index with the acrylics. So this is just introduce about the experimental setup for how to adjust the refracting index, prepare the refracting index for our experiment. And also the working fluid condition in this experiment should have the same Reynolds number in both of the numerical simulation and also the experimental measurement. Because in numerical simulation we use the air, but in our experimental working fluid were the poly tungsten. This is one kind of a chemical to put into the water and mixing, so we can have the a mixture, and then the mixture with the good refracting index with the acrylic, and then we can perform the PIV measurement with the good quality of image. And this is the velocity vector maps at mid planes of human airway. This is the experimental result. We did for the 7.5 liter per minute. This is in the resting condition, and for 15 liter per minute of inhalation. It's just for the inhalation of the human airway. This is the defined for the light working, and for 30 liter per minute. This is for intensive working of the people. And we can see the velocity map from the left to middle to the right, and of course increasing the inhalation flow rate, the velocity vector also increasing the length here. Now we will move to the computational fluid dynamics. This is also very important work for us. Yes, let's talk about the CFD simulation. Computational fluid dynamics is the science of predicting phenomena in our life by solving the mathematical equation using computer program, including fluid interaction, fluid solid interaction, and also fluid gas interaction. And yes, on the left figure is mixing water and oils in the tanks, and in the middle animation is a solid cylinder dropping into a bucket of fluid, and on the right figure the blowing air from the bottom in a column. And this is one of the very important thing for the fluid dynamics is the application. We should find application here, and this is the some application in aerospace, oil and gas, automotive, process industries, wind turbine, aerodynamics simulation. We can calculate the drag coefficient, the drag force due to the racing car, and we can see the turbulent flow at the back side, at the rear side of the car. And for the airplane, we can calculate the one shear stress around the Boeing 737 body. Yes, we can calculate the one shear stress. And for the right hand side, we can compare the turbulent vortex between a sphere and a golf ball when we perform some sport activity. Recently, we can apply the CFD simulation for athlete. We can make a very good swimming suit based on CFD techniques, and also we can create some helmet for the bicycle racer or biker to reduce the drag coefficient and enhance their speed during the race. We can apply for in the biomedical field. Like here, we can see we can perform for the hip replacement implant simulation. Right? This is we can do prior to we perform the surgical surgeon, and we can perform for heart and arterial simulation, and we can do for the human respiratory tract simulation. Let's talk about this later. And the computational fluid dynamic numerical simulation approach is based on the concept regarding the Eulerian approach. It's describe the fluid motion. This we consider how flow properties change at a fluid element that is fixed in the space and time. We call this Eulerian. But in the Larassian approach, is different. The fluid flow field is comprised of a large number of finite-sized fluid particles which have mass, momentum, internal energy, and other properties. And the mathematical laws then be written for each fluid particle. So in the Larassian approach, the particle moving from this side to that side during the time, we can got the trajectory of the moving. So we can call it path line. This is a governing equation of Eulerian approach. The numerical modeling of airflow involves the solution of Navier-Stokes equation that we mentioned before, and the fluctuating around mean value has led to develop a turbulent model which rely on a process called Reynolds average Navier-Stokes averaging. So at first, it's based on the conservation of mass, and also it's based on the conservation of momentum. And in our calculation, we assume that the Reynolds scale is proportional to the mean velocity gradient. So we can calculate here. And in our equation, this is the nu t. Nu t is mean the SD viscosity coefficient. And in the nu t, it's based on the C mu n. This is based on the C mu n F mu. And based on this coefficient, we can use the various kind of the turbulent model to define for SD viscosity coefficient. In turbulent flow, the velocity, pressure, and stress are constantly fluctuating. Then in our calculation, we also apply the Lagrangian decreased phase model. The trajectory of decreased phase particle can be calculated by integrating the force balance on the particle. It can be written in a Lagrangian reference frame. For example, this is the particle velocity can calculate based on the drag force. This is the defined for drag force, and this is defined for gravitational force, and this is for the thermophoretic force, and also buoyancy force and submarine force. And based on this calculation, we need to identify the particle Reynolds number and also the drag coefficient here to calculate for this equation. Yeah, we just keep in mind that this is just for the drag force. This is for gravitational force. This is main force for acting onto the one of particles in the still air. Let's move to the simulation. After we got all of the approach, and then we can perform the simulation. And this is one of our trial, one of our attempt to calculate the upper human airways. This is the airflow distribution in the nasal cavity. And in this figure, this is a coronal plane, through the nasal cavity of Asian guys for the inhalation mode, not exhalation, only inhalation. And we can see the air pass through from this side, from the bottom to the top, from bottom to the top, and then moving in within this plane, these planes. And this is A, B, C, D, E, F, G. Yes, it's become narrower from plane C, and D and E and F and G a little bit wider. Of course, on the left hand side, the higher velocity occurs. We can see here the higher velocity on the left hand side, left turbinate. Yes. When we do the simulation, we didn't know how much accuracy of our calculation. So we have to check, we have to validate the numerical result with the experimental result. And fortunately, we found that a PIV measurement is really best match for us. And we conduct PIV measurement to get the PIV data for the human airway in the trachea region. This is for the trachea region. And on the left hand side, PIV data, and on the right hand side, the CFD prediction. A little bit different, but however, we can compare the magnitude, velocity magnitude, and it's look a little bit similar of PIV, between the PIV and CFD prediction. And all of the velocity we normalize by the inlet velocity. And here we can see is a realistic shape prove that the remarkable phenomenon of inclination, right? It is inclination, the high velocity in this side and low velocity on the right side here, and the maximum velocity found both of the downstream of the simulated and experimental data. And of course, in overall, we can make conclusion that the experimental data and simulation data agree well together. Okay, after we did for the numerical validation, and then we can apply the CFD simulation for various of the case study, and we to evaluate the impact of the air pollution on human upper airways. Yes, at first we focus on the particulate matter because it can be toxic, one of toxics. Because of the particulate matter can enter the lungs, interfere cleansing mechanism of respiratory tract, and particulate matter can be intrinsically toxic, mix of toxic material. Particulate matter can act as the carrier or absorb toxic substance. And of course, small particles have a large absorption surface, and fine inhalable particle contain more toxic than the large particle. And this is some our simulation result. On this slide, this is the trajectory of representative particle. On the left screen is the particle simulation for model A, and the right hand side model B. Model B is a Caucasian guy. Model A is Asian guy. We have a little bit compare. Between Asian and Caucasian. Who will be more risk than the other one. And finally, our result. That's one have published into the Indoor and Built Environment article journal, and we found that a very interesting that the Asian people exposure higher risk than the Caucasian model. And yes, let's have a look for the particle of 1 micrometer. For the PM, this is 1 micrometer on the upper and 10 micrometer on the lower. For the 1 micrometer, it's almost the particle transport to the trachea, almost from here. This is a release area, and particle release here and transport move to the nasal cavity, the nasopharynx, larynx, and this is from here trachea. And yes, and this is for 10 micrometer. However, in the model B, at the same flow rate, 30 liters per minute, is a higher velocity here, and this transport a little bit turbulent occurs here, a lot of particle moving here, and we can see the number of particle moving down to trachea like this. And for the 10 micrometer, the number of particle moving to downstream is less than for in the model A. This is one of the interesting result of our study. It means that in the model B, a number of particle of 10 micrometer move to the downstream to the trachea here less than in the model A. It means that in this region working better than in model A. It can capture the particle of 10 micrometer PM10 in the nasal cavity well. And this is a visualization of hotspot deposition. The last slide were the trajectories. This is the Hotspot, it means that the number, the location, deposition location of the particle. We have 7.5 liter per minute. This is 30 liter per minute. And this is 1 micrometer, and this is 10 micrometer. And because the number of particles here is very few, because of the 1 micrometer, mostly particle transport to the lung, and here the particle of 10 micrometer deposits here, because it's quite large compared to 1 micrometer, and it can be captured in this region. And for the model B, we can see the number of the particle trapped in this nasal cavity higher than in model A. And also in this case, for the model B is also the number trapped in this region higher than in the model A. And this is a local deposition fraction. Yes, based on model A and model B, we can see for 7.5 liter per minute to 30 liter per minute here. And of course, in the this region, higher deposition rates in this region, nasal cavity is working very well. Then this is the animation of me for the unsteady particle inhalation. This is 10,000 of ultrafine particle. It means around 0.1 micrometer. Yes, we did various range of particle size from 100 micrometer to down to the nano scale or ultrafine particle scale in our simulation. And this is one of the animation for ultrafine particle simulation in the human airways. And you can see, yeah, it's very small particle, and it's mostly transport down to the trachea and to the lungs. It's not deposited into our upper airways. And of course, in our human airway, we have the cleaning mechanism. It means the clearance mechanism. So for coughing, it is a cycling, and this is for the trachea and bronchus. The rate of cleaning is instantaneous. For ciliary, for left bronchi, bronchial and bronchial airways. And for macrophage in the alveoli or air sacs. And for lymphatics is for lung tissue. And the rating of cleaning a month or years or very, very long time for cleaning. And this is one of the recent result for CFD. This is the one of our room in Ho Chi Minh City University of Natural Resources and Environment. This is the inlet. This is the inlet, and the inlet velocity here, and it's transport to the outlets here. And we assume that there are 3 persons sitting in this room, in our room. And I try to show, but I don't know how to show. Just a moment. Yes, here. This is one of our simulation for the coughing of droplets transport from the mouth to the opposite person. And we can see the transportation of the droplets within few seconds. And it just reminded for the patient of virus infected by virus or COVID-19. This is very dangerous for us when we contact very close like this. And yes, yes, what should we do in the next day? Of course, PIV result was used for the validation with the CFD simulation, and this work can be used for development of in silico model And CFD study using in silico human airway model expressing the profound impact of airway structure on the airflow pattern and deposition fraction. And computational simulation have a great potential to contribute to study of therapeutics, drug delivery, and inhalation toxicology for human. And also applying of PRV and CFD can develop the technical support to assess the impact of air pollution to human health and provide guidance on effective intervention to improve health and air quality. Yes, and thank you very much for your kind attention. I hope you enjoy my talk, and I'm very happy to answer any question you might have.
Yeah, thank you a lot. The talk was indeed the most enlightening and exciting. I learned a lot. Thank you for great slides and for sharing your experience. So this is the answers and questions time. Anyone has questions right now? I guess this time we even can take questions in Vietnamese, provided that someone will translate them for the audience that doesn't speak the language.
Hi, I have two questions. First of all, thank you very much for the presentation. Very useful. My first question is, what is a good model to, for example, student to simulate CFD? And my second question is, I'm not quite understand why we can determine the probability of the highest probability of an apathic based on the scan picture, because as you saw from the position of previous picture, we have equal probability for several dots outside. So how can we finally find the highest probability of the moving of the particle? I cannot figure out this point. So
Okay.
that's my question. Thank you very much.
Yes, I realize. Yeah, thank you very much for your question. I realize to see your the audience, but I cannot find how to show the. Okay, so now yes, can you see my slide? Or I cannot see you in Zoom. A little bit confused for me.
I can see the slide and the video. So you just have to choose some gallery, some kind of view.
Okay.
In the computer.
Okay. Thank you very much. Yes. Yes. Your question is very interesting because I attend the international conference. Yes, and I have a talks with a very famous professor in the Building and Environment channel. He's the editor in chief of the channel, and we try to discuss about the most appropriate model for for our simulation. But he said that there are no universal model for us. I mean that we need to specify the problem, and then we can choose the model, and then we can testing our model, and then we can disclose our model is appropriate for that kind of problem. That can solve the problem. There are no universal model for simulation. This is my answer.
I see.
Yes.
Yes. So can you just suggest some model so people can investigate?
Yes. For example, in the build environment, I mean that's in the enclosed space and enclosed space in a room. We uh, try to find a very good way, but uh, is it the computer burden? For example, you can do for LES um, model. This is large edge simulation model. So a large edge simulation model is very well, but it's time consuming and also the uh, computational burden problem. We need to do the super computer simulation, and this is our problem. Uh, yes, yeah, of course, I suggest you to use the LES model for simulation. Mm. And one of my students now try to do the LES. He's doing a PhD course in Korea, and now he's still working with me, cooperate with me to do the LES, and he will he can do it and can share the result in the near future, but it takes time for the LES. And for the engineer, yes, for the second suggestion is for the engineer, we can choose for two equation turbulent model like standard K epsilon model, but standard K epsilon model is a little bit low prediction accuracy, and we prefer to use the low Reynolds K epsilon model, or low Reynolds K epsilon model, so we can do for the SST K omega turbulent model or something like that. Yes, of course we have a lot of validation for the standard K epsilon model, INZ K epsilon model, SST K omega model, low Reynolds Abe Kondo Nagano model. We did a lot. Yes, and I suggest you to use a low Reynolds K epsilon model for the simulation.
Thank you. What was the answer to the question?
Yes, it's helped a lot. Thank you very much. For it's my first question and the second question.
Please. Yeah, please go ahead with the second one.
So my second question is, how can we determine the most probability position of one particle? You show that we have from the quite previous slides. You show that when from the first scan picture to the second scan picture of the particle, then we can do the probability, and then we can find the most probability position of particle. But I still very wonder why, how can we calculate that?
Okay, so I will show you one more slide, and then we can discuss regarding this because my animation didn't work. So I will be back to that slide and show you. Now you can see my screen, right? My slide,
Yes.
right?
Yes,
Okay.
yeah, I can see it very well.
Okay, so can you see this?
Yes, I can see this one very good image.
Okay, this is one of the animation I did it. I did it for PIV visualization. Okay, this is the first one. This is not include the vertical duct, not include the buffer plate, and the second one including the buffer plate. Yeah, there are some vortex occurs in above the buffer plate.
Yes.
Okay, So when we set up the time step between the first frame and second frame, in my case, we did for 500 frame per second. 500 frame per second. It means around 0.2 millisecond, right?
Yes.
Around 0.2 millisecond. Yes, and between first frame and second frame are only 2 millisecond, and then based on the time, we can use some correlation, a cross correlation algorithm to calculate the in each interrogation area, very small area, around 20 tracer, 20 particle inside, and then we calculate the particle from first frame and in the second frame, very short time, and then we can identify which is the best match for the tracer from that ship, from the first and the second. And it's just very small ship, and then easier for catching the best match. This is our calculation.
So it means that in the mathematical we have something related with the distance from.
Yes.
So yeah, that's so it's clear for me now. Thank you very much.
Thank you.
Thank you.
Any other questions? I think we still can take one very quick question. As I mentioned, this time we also can take a question in Vietnamese if someone would translate it. Okay, but your talk was extremely clear, and that's, I believe, the reason why we don't have questions now. Thank you again for being with us. Thank you, everyone, for attending this session. It was very enlightening and useful, even in practical terms. And welcome to the our session on the next week. We'll have Professor Rob Youngman of Wageningen University and Research Center from the Netherlands, who is probably the world's greatest authority in ecosystem connectivity. So he will give his talk on this particular topic. So thank you again, everyone, for being a part of our webinar series, and let's stay in touch. Thank you. Bye.
Yeah, thank you very much.
Bye bye everyone. Thank you, Anh
Yeah,
Phương.
bye bye. Yeah, thank you, Thủy.